In this video, we compute the torque on a loop of current in a magnetic field, and then we illustrate the basic concept of how a DC electric motor works. First, we consider a rectangular loop in a magnetic field, and you can see I've labeled the length of this thing with an L and the width of it with a W, and we're using a rectangular loop just for the simplicity of the geometry. I have a current of I flowing through this loop, and I have two permanent magnets. I have a north pole on this side and a south pole facing this side. That creates a magnetic field straight to the right across this loop. Note that I used a dotted white line here to represent the axle that the loop is free to spin on. Viewed from above, the loop looks like this. And I've labeled a vector called n. That's called a normal vector. It points perpendicular to the area of the loop, and we're measuring everything with respect to that, and it's making an angle of theta with respect to the magnetic field direction. If I compare my first picture to my second, back here I had the current going up, and when I look at it from above, I see the current coming out of the page. On this branch, I had the current going down. So when I look at it from above, the current's going into the page. And across the top branch of the loop, the current is going this way. And the bottom branch has been obscured by the top branch, so we can't see that. Now, just viewing current as a flow of positive charge, I can use the right-hand rule for the Lorentz force law and find the direction of force on this branch in which the current is coming out of the page. I put my fingers in the direction of current, I sweep out to the direction of the magnetic field, and I get a force vector pointing up. If I do the same thing on the current that's going into the page on this other branch, putting my fingers in the direction of current, sweeping out to the direction of magnetic field, I find that the magnetic force is downward on that branch. Now, each of these forces creates a counterclockwise torque on the loop with respect to this rotation axis in the center, and we'll get back to that in just a second. But I want to look at the top and bottom branches in our original picture, this one and this one, before we get into calculating the torque. So I'm going to put my fingers in the direction of current on this top branch, sweep out to the direction of the magnetic field. And that gives me a magnetic force pointing out of the page. Well, that force can't exert any torque with respect to the rotation axis. It's simply trying to stretch the loop upward. If you do the lower branch, the current's in the opposite direction. The force is going to point into the page, and that magnetic force is trying to stretch the loop out downward. So in the top and bottom branches, the magnetic force exerts no torque. It just acts to try to stretch the loop. So we can forget about the force on the top and bottom branches. Our torque is created only by these two forces that I've already labeled on the current coming out of the page and going into the page. The first thing I want to accomplish is to find the magnitude of that force. And in a previous video, and I'll post a link to it right now, we computed the force per unit length on a current carrying wire. It turned out to be IB sine theta, where that angle is the angle between the current and the magnetic field. This is not the same theta I have labeled in my picture here. It's the angle between this current and the magnetic field. With the current coming out of the page and the field pointing to the right, those are perpendicular. So theta is 90 degrees and sine theta is 1. To find the force on a little branch then, you would take IB multiplied by the length of that little branch of wire. And so I get IB times L, because that's the length of one of these branches that points vertically. Now I need to find the torque exerted by that force. I can see it's going to be a counterclockwise torque. I'm only going to analyze the torque exerted by one of these forces, and then I'm going to double the result, just taking advantage of symmetry here. And in order to find a torque, I've got to get the perpendicular component of that force. Well, this gets me into a bunch of trigonometry, because I need to relate this angle to theta, and then I'm going to take f times the sine of theta to get that perpendicular piece. So I've drawn a horizontal dashed line here. I've drawn a perpendicular to the face of the loop, and that means this angle is theta. But this angle and this angle add up to 90 degrees, and that means this angle is 90 minus theta. But that 90 minus theta added to the angle of interest over here is equal to 90 degrees. So what do I add to 90 minus theta to get to 90 degrees? It must be theta. This is so similar to the trigonometry we had to work out for inclined planes. It's all the same stuff. So it turns out this angle that I labeled is theta up here, the same as the angle between the normal vector and the magnetic field, and the perpendicular piece of the force is going to be F sine theta. And we'll go ahead and translate that perpendicular piece over here so it's attached at the edge of the loop. Again, that's F sine theta. And again, I'm trying to compute the torque here, and I'll post a link real quick back to where torque was first introduced. But in order to get the torque, I've got to get the lever arm between where the force is exerted and where the rotation axis is. We normally call that an R. Well, in this case, that's just W divided by 2. So now I can write down the torque exerted by one of these branches, and it's going to be F sine theta times W over 2. Remember, that's only half the total torque, so I need to multiply by 2. It's just going to undo the 2 right there. Then I plug in the fact that F is given by IB times L, and I'll move my W out in front of the sine theta. And I've got the torque exerted on the current loop, but there's more progress to be made here. We want to generalize to things that aren't necessarily rectangles. I recognize length times width here is equal to the area enclosed by the loop. And this is actually how it generalizes. If I had a circular loop, then I would just use the area enclosed in that loop to do the torque calculation. Notice that this torque is going to be maximum when the loop is parallel to the magnetic field. In other words, the normal vector is perpendicular to the magnetic field. So tau max happens when the normal vector is perpendicular to the magnetic field, which means the loop is parallel to the magnetic field, and that's just IBA. And then tau will go all the way to 0 if my angle is 0 or 180 degrees, indicating that the loop is perpendicular to the magnetic field. Now, to understand what's going to happen qualitatively in terms of the direction of the torque, it's nice to not have to go back and do all this force analysis every time. Instead, we apply the right-hand rule for Ampere's law in order to visualize which way the magnetic field lines are going to be coming out of this loop. So if I put my thumb in the direction of current along the top branch, my fingers are going to curl around in the direction of magnetic field. And this means that magnetic field lines are coming out through the area of the loop in this direction and then wrapping around the loop. So it's hard to show that for the vertical lines, but along the edges over here, the magnetic field lines would wrap around this way. With field lines coming out of the interior of the loop in this direction, the same direction as the normal vector, by the way, we can represent this as a magnetic dipole. In other words, it's kind of like a tiny bar magnet, field lines emanating from the North Pole and then coming into the South Pole. So we can just use a little vector to visualize this as a magnetic dipole. And then we could summarize what's happening in terms of the torque by just saying, well, all that's happening is a little north-south magnetic dipole is trying to line up with the magnetic field that we exposed it to. So if we go back and look at which way the torque was exerted in our calculation, it was a counterclockwise torque. That's really just a magnetic dipole trying to align with an external magnetic field. That makes it way quicker to analyze the situation on the right. And on the right, I've shown the basics of how an electric motor works. Basically, you have coils of wire rotating in a magnetic field. You're running a current through those coils of wire to get the loop to interact with the magnetic field. In our first picture, the magnetic dipole is pointing down and to the left, and that's going to try to align with the external magnetic field. In other words, the whole thing is going to twist this way. The torque is shown as counterclockwise. Eventually, the dipole ends up aligned with the magnetic field, and at this point, it might wiggle back and forth a few times and just settle down and stay pointed that direction unless we do something. So the clever trick of an electric motor is to suddenly switch the direction of the current. So momentum carries this coil through the equilibrium position just a little, and that's what we're looking at in the third picture. But you'll notice the part that was an outward current has just switched to being an inward current and vice versa. That flips the direction of the magnetic dipole of this loop. And now again, if I look at the torque on it, the torque is going to act in the direction that tries to align it with the external magnetic field, and it's going to be another counterclockwise torque. So by constantly switching the direction of the current, every time this dipole arrives at its equilibrium position, we can continue to have the loop flip and flip and flip and flip, and this is the basis of a DC electric motor. So it's a little tricky to understand, well, how are we going to just flip the direction of current in a loop every time the loop flips? And the answer is that we use a device called a commutator, and that's this little gray thing I've shown at the top of the final diagram. You have the wire from the loop soldered to one side of the commutator, at the other end of the loop soldered to the other side of the commutator, and those are two half rings that are attached to some kind of shaft. The little black line here is a gap, an insulating gap between those rings so they don't short out. Then the positive side of the battery is connected to this spring right here. Those are called brushes. Negative side of the battery to this spring right here. And those springs slide along the commutator as it rotates. Now, every time the loop flips by 180 degrees, current reverses direction in the loop. And this is how you get this continuous flipping behavior to occur. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.